In our previous lesson in this series, we discussed and analyzed merge sort algorithm. Merge sort, as we saw, is a recursive algorithm in which we follow a divide and conquer strategy. The running time of merge sort is big O of n log n in worst case, but merge sort is not an in-place sorting algorithm. An in-place sorting algorithm takes constant amount of extra memory, but the space complexity of merge sort is big O of n. The extra memory required is proportional to the number of elements in a list that needs to be sorted. Now in this lesson we will discuss and analyze Quicksort, which is another recursive algorithm where we will follow a divide and conquer strategy. Time complexity of Quicksort algorithm is big O of n log n in average case, and it is big O of n square in worst case. But Quicksort is an in-place sorting algorithm. We take almost constant amount of extra memory, and despite having a worst case running time of big O of n square, Quicksort is pretty fast and efficient in practical scenarios. The worst case running time of Quicksort is almost always avoided by using what we call a randomized version of Quicksort. Randomized Quicksort gives us big O of n log n running time with very high probability. Quicksort is often the most practical choice for an efficient sorting algorithm. In fact, sort function given to us by most of the language libraries are implementations of Quicksort only. So in this lesson we will discuss and analyze Quicksort algorithm. Once again, I'll take a very simple sorting scenario. Let's say we have a list of integers given to us in the form of an array, something like this. I'll name this array A, and we want to rearrange this list in increasing order of the value of integers. Now in Quicksort, what we do is we first select one of the elements from the list, and this can be any element. In this example here, let's say we select number 4. Now we call this selected number pivot, and now first we rearrange the list such that all the elements lesser than the pivot are towards the left of it, and all the elements greater than the pivot are towards the right of it. Something like this. Let's call this whole process partitioning of a list. So let's say partition is a process in which we select a pivot and rearrange the list such that all the elements lesser than the pivot are towards the left and all the elements greater than the pivot are towards the right. There can be more than one possible arrangements in which elements lesser than the pivot will be towards the left and elements greater than the pivot will be towards the right. For example, 2, 1 and 3 are lesser than the pivot in this example. We could have had them in order 3, 2, 1 or 1, 2, 3. It doesn't really matter. We can have any one such arrangement. The only requirement is that all the elements lesser than the pivot should be towards left and all the elements greater than the pivot should be towards right. We have an efficient in-place algorithm to partition a list like this. We can do so in constant amount of extra memory using only some temporary variables. We will come back to the partitioning logic, but let's first think about this. Once we have partitioned the array like this, we can break this problem into two sub-problems. And the two sub-problems will be sorting the segment of the array to the left of the pivot and sorting the segment of the array to the right of the pivot. And this time, unlike merge sort, we do not need to create auxiliary arrays, entirely new arrays, and copy the elements into these new arrays. We can work on the same array. It's just that we will have to keep track of the start and end index of these segments. So if this is array A from index 0 to 7, this is segment of array A from index 0 till 2, and this is segment of array A from index 4 till 7. We will come back to why we do not need to create auxiliary arrays and why we can work on the same array, just marking the start and end of a segment. Let's first try to understand the core logic. So far we understand that once a list has been partitioned, then we have two sub-problems to solve. sorting the list left of the pivot and then sorting the list right of the pivot, sorting the sublist left of the pivot and sorting the sublist right of the pivot. But now how do we sort these two sublists that we have created? We can apply the partitioning logic once again and break the problem even further. Let's say first we want to work on this left sublist. So we choose a pivot and then we rearrange this sublist such that all the elements lesser than the pivot are towards left. 3 is the largest in this sublist, so this arrangement is actually satisfying the condition. And this problem will actually have only one subproblem. Now we need to work on segment of the array from 0 till 1, because there has to be a deterministic logic of picking up the pivot. Let's say we always pick the rightmost element in the sublist as pivot. So for this segment from 0 till 1, we will pick 1 as pivot, and this sublist will be rearranged like this, and we will have one subproblem to solve. So we are going on in a recursion. We are breaking the problem in self-similar manner. And remember, all the rearrangement is happening in the original array only, in the original list only. These segments that we are showing here are just snapshots of the original array. So at this stage we have 2, 1 and 3 at 0, 1 and 2 respectively in A, and when we go to this stage after partition, 2 goes to index 1 and 1 comes to index 0. So when we are here, when our segment is only one element, the element at index 1, then the original array from index 0 till 2 is 1, 2 and 3 at indices 0, 1 and 2 respectively. And when we have only one element in a sublist or a segment, that segment is already sorted. We do not need to break the problem any further. So we need to stop our recursion at this stage. This will be the exit condition from recursion. And at this stage, the segment from 0 till index 2 is sorted. And now we can go ahead and work on the segment from index 4 till 7. Now let's first try to understand how we will do all of this programmatically. I will write a function named Quicksort that will take as argument an array A and start and end index of the segment that needs to be sorted. Now why do we need start and end as argument? Because we do not want to create any auxiliary array, any new array. What we want to do is we want to use the same array. We want to keep on passing the same array, and we just want to mark the boundaries of the segment that we want to work upon. Initially we will call the quicksort function passing it start index 0 and end index length -1, so we will pass the whole array. Things will be clear when I'll write the body of this function. Now in this function, first we will make a call to partition the array, and to partition also we will pass the array, the start index and the end index, to tell that you need to work only on this segment. Now this function partition, let's say, will rearrange the array such that we'll rearrange the segment of the array from start till end such that there will be a pivot and all the elements left of the pivot will be lesser and all the elements right of the pivot or towards the higher indices of the pivot will be greater. And let's say this function will return the index of the pivot after rearrangement. I will call it P index for partition index. Now once we have rearranged a segment in this process partition and got the partition index, the index of the pivot, then we can make two recursive calls, one to sort the segment left of the partition index and another to sort the segment right or towards the higher indices of partition index. So first call is for segment start till partition index -1, and another call is for segment starting partition index +1 till end. There is only one thing remaining here now. We do not want to go into the recursion infinitely, so we must write a base condition or exit condition in our function here. As we had seen, we can exit if a segment is having only one element. So we can write something like this: if start of the segment is greater than or equal to end, then we can return, which will mean exiting the function. Why start greater than or equal to end and not just start equal end? Well, start greater than or equal to end will take care of two things. If the segment is invalid, then also we will exit, and if segment will have only one element, then also we will exit. Sometimes we will not have a valid segment in the left or in the right, like here for this segment from index 0 till 1, there is no segment left to the pivot, but still we will make a recursive call to quicksort. We need to gracefully exit. In that case, we can also write something like this: do this whole partitioning only if start is strictly less than end, and this will also mean the same thing. We will come back to partitioning logic, which is the core of this algorithm, but first I'll quickly simulate a run of quicksort on this example array here. First we will make a call to quicksort, passing it array start index 0 and end index 7. Now start is less than end, 0 is less than 7, so partition function will be called, and after partition index will be 3. So this quicksort call will make another quicksort call with start index 0 and end index 2. Whenever a function makes another call, the execution of that particular function call is paused. The machine says that, hey, I'll come back to you once I'm done, once I have finished this another call. I'll simply write Q here as shortcut for quicksort. Now once again 0 is less than 2, so we will partition, and this guy QA02 will first make a call to QA01. The state of execution of this call will be paused. We will go to QA01. 0 once again is less than 1, so partition will run. We are already showing the partitioned segment here, and first a call will be made to QA0, and partition index here is 0, so we will make a call like this. Now start equals 0 and end equal -1 is an invalid segment, but our code is taking care of it. We will not go inside the if condition here for this particular call, and this particular call will simply finish and exit. So this guy will simply return without doing anything. The control will return back to QA01, and now this guy will make another recursive call to QA11. Now once again for this guy, start less than end condition will be false, so this guy will not partition, it will simply return, and now QA01 will return, and now QA02 will make another call to QA23. Sorry, A32, it has to be P index +1 till end. Once again this is an invalid segment, so this guy will simply return, and now QA02 will return, QA07 will resume, and now QA07 will make a call for the segment right of the pivot. A call like QA47 will be made. 4 is less than 7, so first partition will happen. After partition, pivot will be 5. Now QA47 will make call to, it will first make a call like QA start 4 end 4, which will simply return because we have only one element in the segment. Then it will make another call for segment from 6 to 7. This guy will again make two calls, one for an invalid segment, the right one will be for invalid segment, and one for the left one. First it will make a call for the left one. The left one will have one element in the segment, so that will also simply return. So finally with all these calls, our list in all will be sorted. Once the right sublist is also sorted, the list itself, the overall list, will also be sorted. So this is how things will happen. This is how things will execute for this recursive function quicksort. Now let's talk about the partitioning logic. Basically we want to solve this problem. We want to select a pivot and we want to rearrange a list such that all the elements lesser than the pivot are to the left of it and all the elements greater than the pivot are to the right of it. I want to write a function named partition that should take an array, the start index of the segment in the array that needs to be partitioned, and the end index of the segment. This signature will make sure that we have a function to partition a segment of array A. You can pass the whole array to this function, or you can pass a segment. You just need to pass the right values for start and end. Now in this function we first need to select the pivot. Let's say the rightmost element in the segment is selected as pivot. So pivot is always A end. If we pass this whole array, we will pass A, start will be 0, end will be 7. So pivot will be 4. Now partition logic will be something like this. We will first take a variable named p index or partition index. I'm just writing shortcut p index for partition index, and initially we will set it to start. And now we will scan the whole list from start till end -1, and we will make sure that all the elements lesser than the pivot are pushed to the left of partition index. Partition index will be adjusted accordingly. So we will do something like this. We will run a loop from start till end -1, and if the element at that particular index is less than or equal to pivot, we will first swap that particular element with the element at partition index, and then we will increment the partition index. With this much of code, let's quickly see what will happen if we will try to partition this array that we are showing in the left here. We will pass this array. Start index will be 0, end index will be 7, so 4 will be the pivot. P index will initially be 0. Now the idea is to push all the elements lesser than the pivot to the left of p index. We will start the for loop with I equals 0. We will come to this conditional statement. 7 is not less than or equal to 4, it is greater than 4. So no swapping will happen, I will simply get incremented. Now AI will be 2, 2 is lesser than 4. So we will swap the elements at index I and at index p index, and now p index will be incremented. At any stage, all the elements to the left of partition index will be lesser than the pivot. Let's say we will show them in this blue color. Now I will be incremented, I will be 2, 1 once again is lesser than 4. So we will swap these two elements, 7 and 1. Partition index will now be equal to 2 and I will be 3. 6 is greater than 4. So we will simply move. 8 once again is greater than 4. I will now be 5, and 5, the element at index 5 is also greater than 4. So we will go to index 6. 3 is lesser than 4, so we need a swap here. And now p index at this stage will be 3, and now we will exit the for loop. And if you can see, at this stage all the elements lesser than the pivot are towards the left of the partition index, and the pivot itself and the elements greater than the pivot are on or after the partition index. Now there is only one more thing that we need to do, and we will have a proper partitioning. We will swap the element at the partition index with the element at end index, which is the pivot. So 6 will go to index 7 and 4 will come to index 3. And now we have a proper partitioning. This function partition will return the partition index, and we are good. With this implementation of partition function, the quicksort function that we had written earlier will work. Let's quickly write a real program for this and see whether this works or not. I'm writing this program in C++. This is the implementation of partition function, and then I have written the quicksort function. Inside the quicksort function we make a call to partition, and then we make two recursive calls. In the main function I have initialized an array of 8 elements. Then I'm making a call to quicksort, passing starting index 0, end index 7, and then I'm simply printing the elements in the array after call to quicksort. Let's see what happens when we run this code. The output seems to be sorted. Now let's change this array. Let's pick up the example that we had used earlier. This is the array that we had used in our example. Once again, the output seems to be correct. So we are looking good. So this is our implementation of Quicksort in C++. We have left one question unanswered. The question was why are we not having to create an auxiliary array here like merge sort? Well, in merge sort, once we were done sorting the left part and the right part, then we were merging the two parts back into the original list, and there is no way you can perform the merge process without using auxiliary arrays. Think about it and you should be able to get it. We will analyze the properties and running time of Quicksort in next lesson. This is it for this lesson. Thanks for watching.